Welcome to the series of design of steel structural elements. So, in the last session, we had worked out a design problem of a cantilever beam, which is laterally supported with UDL. Okay. In this session, we will solve a problem of simply supported beam with UDL. So we'll also design the same, and this beam is also laterally supported. So let me share my content. So I'll read out the problem. A roof of hall measuring 6 meter by 13.7 meter consists of 120 thick slab. Thickness of the slab is given to calculate the dead weight of the slab. Supported on steel I section spaced at 3.5 meter center to center, and the hall is having a wall of 30 centimeter thickness all around, and the finishing load on the roof is given as 1 kilonewton per meter square per meter directly, and live load is given as 2 kilonewton per meter square. So design the steel beam and apply all the necessary checks on the design. So here, there's a sketch here. You can see here the dimension of the hall is 6 meter wide and 13.7 meter long. And the beams are spaced at 3.5 meters center to center. So I have taken one beam, and the load acting on the beam, half of the load from this width will be coming on this beam. Similarly, half load from this. So total width of the load that you have to consider, width of the slab load you have to consider on the beam is 3.5. 3.5 by 2 this side, 3.5 by 2 this side. So let us calculate the load first. That is the first step. So first we have to calculate the self weight of the RCC slab. The thickness is given as 120. So it in meters it is 0.12 meters, and 1 meter length is taken, and 3.5 meter is the width of the slab. So into density of concrete, that will come to 10.08 kilonewton per meter. So per meter length of the per meter along 1 meter length, the weight of the slab is 10.08 kilonewtons. Then the finishing load is directly given, so you can take it as 1 kilonewton per meter on the beam, and self weight of the beam can be taken as 1 kilonewton per meter. So this is the total dead load, finishing load plus slab weight plus self weight of the beam. You can assume it as 1 kilonewton per meter. So total dead load is 12.08 kilonewton per meter. So live load on the beam is given as 2 kilonewton per meter square. So it will be acting over a width of 3.5 meters into 1 meter length of the beam. This comes to 7 kilonewton per meter. So the total load is the total dead load and the live load, that is 12.08 plus 7. So that comes to 19.08 kilonewton per meter. But we have to multiply by the load factor to get the factored load. Factored load is 1.5 into 19.08, which is 28.62 kilonewton per meter. So now this is the beam. The length of the clear dimension of the hall is 6 meter wide, but it has got a wall of 30 centimeter thick on either side. So it is zero point 0.3 is from center to center. So effective length is taken as 6 plus zero point 0.3. One side it is 0.3 by 2, the other side it is 0.3 by 2. So totally 0.3. So 6.3 meters is the effective length. So we have to design this beam, and the beam is laterally supported. So maximum bending moment, first we have calculated the load. Second step is to calculate the bending moment and shear force. We know the bending moment in simply supported beam with UDL is WL square by 8. W we have calculated, this is a factored load, 28.62 into span is 6.3 square divided by 8. This comes to 139.331 kilonewton meter. Not it is per meter. The unit of bending moment is kilonewton meter. I'm sorry about this. Shear force is WL by 2. which is equal to W is 28.62 into 6.3 by 2, which is 88.45 kilonewtons. And so from the equation which is given in the code book, which we have already discussed, so MD is equal to what? ZPFY divided by gamma M naught. So from that we are writing this ZP. So ZP is equal to M into gamma M naught divided by Fy, where beta B value is 1 because it is assumed as plastic section. In the beginning, we'll take it as a plastic section, and we'll calculate the ZP. So, substituting the value of moment, that is 139.31 into 10 power 6, converting it into Newton mm. Gamma m naught is 1.1, partial safety factor, divided by yield stress is 250, which is equal to 612,964 mm cube, or 612.96 into 10 to the power of 3 mm cube. So now we have calculated what is the section modulus required for the uh, mm, what is the section modulus required for to take up this bending moment. So now we have to choose a section having a section modulus greater than this. So this formula is given in the code book, which we have already discussed in the design steps. So you please refer the page number and mm, page number and the class of the code book. Okay, selection of trial section. So selecting a section which has got a ZPZ of 1022.9 into 10 to the power of 3, which is greater than 612.96 into 10 to the power of 3. So I've chosen ISMB 400 at the rate of 604.3 Newton per meter. So this has to be taken from code book again, and EZ values also note down similarly, because you will be needing it to calculate uh, you know beta value. So if this will be 1175 into 10 to the power of 3 millimeter cube. Then and also note down the properties of this particular section. Depth of the section is 400, width of the flange is 140, and thickness of the flange TF is 16 mm. Thickness of the web is 8.9 mm, and R is 14 mm. Radius at the root, because we have to calculate the depth of the web, which is equal to 400, the depth of the whole section, minus of 2 times the flange thickness, because the section will be like this. So if this is a section, so there will be root radius. One side I'm writing the filleted edge, the other one is sharp edge. You have to calculate this. So if this is the thickness of the flange, which is 16 mm, and so you have to deduct 16 and, of the compression flange, 16 of the tension flange, plus there is a root radius here, that on both top and the bottom, under the top and the bottom flange it is filleted. The root radius is 14 mm. Yeah, 14 mm. Yes. So you have to deduct that to get the actual depth of this web, D. So this D you can obtain, that comes to 340 mm. So after that we have selected a section. After selecting the section, you have to classify the section whether it belongs to plastic, compact or semi-compact. So for that you have to find out the ratio of B by TF, B by TF, B by TF. So B by TF is 70 by 16. What is this 70? B is BF by 2. Width of the flange divided by 2. Width of the flange is 140 divided by 2, that is 70 divided by 16, which is equal to 4.375. It is less than 9.4. It is less than 9.4. And D by thickness of the web is 340 divided by 8.9. This you have to take the depth of the web only. So that is 340, which we have calculated here in this step, 340. divided by thickness of the web, which is less than 84. If it is less than 9.4 and 84 as per IS 800, so you can classify the section as a plastic section. The design steps is given in the session third session, so you can go through that. So you have to refer the table in IS 800 and then decide, then classify the section. Then next, to check the strength of the uh, assumed section. So what section we have sorry, chosen section? We have chosen this section to take up the calculated ZP. To calculated ZP, so ZP was taken more than this. So now we will see what is its design strength MD. MD. MD should be greater than the moment coming on the beam M, which we have calculated, and we have calculated. So now we have to find out MD. Before calculating MD, we have to check whether it is a beam of low shear or beam of high shear. For that, we have to find out VD, the design strength. So first we have to find out VD. To find out VD, we have this formula. VD is equal to Vn divided by gamma m naught. So for Vn, we have this formula which is again taken from the code book, which is AV into Fy divided by root 3. So where AV is the shear area, which is 400 into 8.9. This is the height of the web, and this is 8.9. So we are taking the height of the web, which is also a part of the flange shear. This height totally we are taking. So the total depth of the section is 400. So this is the web area which resists the shear. So therefore this will be 400 and 8.9 is the thickness of the web into 250 Fy divided by root 3. So that comes to, that is Vn. Substituting that Vn directly here, because Vd is equal to Vn divided by gamma m naught, as I told here. So this gamma m naught is 1.1. Vn I am directly substituting without calculating. So this comes to 467.128 kilometers. So now to know that the beam is section is of low shear or high shear, so you calculate zero point 0.6 VD. 0.6 VD. VD is being calculated now. Calculate 60% of that VD. So that comes to 280.75. So compare it with the shear force of the beam. Shear force of the beam, what we have calculated here, shear force using WL by 2 formula. So you've got 88.45. This is the shear force coming on the beam. So that is compared with zero point 0.6 VD. So 88.45 is less than 280.75. This is also a beam of low shear. So if it is a beam of low shear, we have a formula for MD from the code book. So beta B into ZP into Fy divided by gamma m naught. So beta B value is taken 1 because it is a plastic section, into 1175 is ZP, which is taken, you have to consider for the section whatever you have chosen. So ZP is ZPZ 1022.9. 1022.9 is what you have to substitute here. Okay. Yes, it is 1022.9 is the ZP value. You have to substitute here into 10 to the power of 3. 250 divided by 1.1. 1.1 is, oh, there is interchange of the value. So here there is some mistake. So this is not, this is ZEZ and this is ZPZ. ZPZ. So what I've taken here is correct. What I've taken here is correct. So this is, I'll just erase this. This value is correct. there's a mistake in the previous slide, that the Z, here you have to correct this. This is ZPZ and this is this is ZPZ and this is ZEZ. So you have to take ZP value, because in the formula it is ZP. So it is 1175 into 10 cube 250 divided by 1.1. So MD is 267.04 into 10 to the power of 6, which is greater than 139, the shear force which is coming. Sorry, the bending moment which is coming. So this is the calculated design moment, that is 267.04 into 10 to the power of 6. This is the actual moment coming which we have calculated here, 139.31. So it is greater. So the moment carrying capacity is much higher than what is actually coming on the beam. So it is safe. So then we have to check for the deflection. This is a large step. So delta is equal to, for simply supported beam with UDL, it is 5 WL to the power of 4 by 384 EI. So it is 5 divided by 384 into W is 19.08 into length is the 6300 to the power of 4, and E is Young's modulus into moment of inertia, which you have to take it from the table. So this comes to 9.56 mm. So allowable deflection is effective length divided by 300. So effective length is 6.3 into 1000 converted to mm. This is as per table 6. As for table 6 IS 800, the allowable deflection is given in the table. So you can take this, and for cantilever with UTL it is L by 150. So here it is 300, which is equal to 21. So 9.56 is less than 21 mm. So with respect to deflection also, the beam is safe. Whatever section you have chosen is safe. So this ends session 5, and in the next session we will take up one more problem where the beam is of high shear. So we have solved two problems. One is cantilever retaining wall with UDL, sorry, cantilever beam with UDL, and the second one is the simply supported beam with UDL. The third one also we will say we will take up a beam of high shear, because we have not done that, we have not taken that particular case. So thank you for listening.